We are here for another great event today. Magnimind Academy will continue to offer workshops in a wide range of topics in data science and data-related topics. And if you want to learn more about data science with real-world practices by top-notch instructors, you are all invited to our bootcamps. You can find the details of our program in the chat. Bill Inmon is our speaker today. He is founder and chairman of Forest Dream Technology and best-selling author. He is also known as father of data warehouse. He has written 62 books, and they are sold over 1 million copies worldwide and translated into 9 languages. Bill was named as one of the 10 people who most influenced the first 40 years of computer profession. All right, please join me in welcoming Bill Inmon. Thank you.
Thank you, Abdullah. It's a real pleasure to be here today. Let me see if I can get everything on the screen that we need. Let me get my computer presentation done. Okay. Now let's see if we can share that. Well, let's try this. No. Okay. Let's try this. Now, is that showing the screen, Abdullah?
Yes, it does.
Okay. Well, thank you so much. It is a real pleasure to be here today. I want to talk with you about some architectural developments that are happening in our industry today. As you know, from years past, we started off with basic applications. Then we worked our way to data warehousing. And today we are interested in something called the data lakehouse. So I want to talk with you today a little bit about the origins of how things came to be and what a data lakehouse is. So I want to begin, pardon me, the conversation with a discussion of all data in the corporation. If you go to the corporation today, you will find out there's essentially 3 kinds of data that exists in the world today. There's structured data, there's textual data, pardon me, and there's analog and information analog data in the corporation today. So let's talk about these 3 kinds of data. Each of these kinds of data have their own unique characteristics. And excuse me, I need a little something to drink here. Okay, hopefully that'll be better. Each of the different types of data have their own unique characteristics. Let's talk about transaction-based data. This is the data that most people are familiar with. Transaction-based data is data that usually results from a transaction, such as a bank transaction, point of sale transaction, telephone call, or something like that. And
sorry, Bill, sorry to interrupt it. I'm so sorry, but we cannot see your screen. We just see the directory of your.
Oh, okay, okay. Let's go back and okay, sharing, new share. Okay. Is that better, Abdullah?
Perfect. Thank you.
You can see it now. Okay, I'm sorry, my apologies. Let me back up. I'll try to back up and start again. Let's start with all data in the corporation. All data in the corporation typically looks like something like this. We have structured data, textual data, and analog data in the corporation. And from these types of data, we find out that there's a lot of different characteristics of each of these kinds of data. The first kind of data that most people are familiar with is transaction-based data. Transaction-based data is data that's generated by some transaction occurring, such as a bank transaction, point of sale transaction, telephone call, the making of a payment, etc., and so forth. And so when we have transaction-based data, we typically have such things as records, keys, attributes, indexes, and most people in our industry are familiar with this kind of data, this arrangement of data. The reason it's called structured data is that the same record type is repeated over and over again in a highly structured form and format. Now, there's another kind of data that's out there that's most interesting is textual data. Textual data is found everywhere. Textual data is typically found in places like medical records, contracts, the internet, call centers, email, etc., and so forth. And textual data exists in lots of different formats. It has different languages, English, Spanish, Portuguese. There's different kinds of text, slang, acronyms, formal text. It can exist as voice information, written information, internet information, and so forth. Now, the thing about textual data is most people haven't included textual data in the world in which they operate and work in. And so what we find is that in order to start to make sense of textual data, we need a technology called textual ETL. And textual ETL is the technology that allows us to read text and turn text into a structured format to where the computer can do things with that data. The third kind of data that we have is something called analog data, and it's typically generated by a machine. So we have lots of different kinds of machines out there. There are things like drones, electric eyes, temperature gauges, speed, mechanical forms of collection of the data. I think one of the most interesting examples I've heard of machine-generated data are the uses of drones going over shopping centers to determine how many cars are in the parking lot of the shopping center. And in doing so, people can gauge how much revenue is going to be passing through the shopping center. But there's lots of other kinds of mechanically generated data that's out there as well. So we end up having essentially three kinds of data in the corporation. We have structured data, textual data, and machine-generated data. As an example of machine-generated data, I'll never forget the first place I ever worked was in a missile range in New Mexico. And in this missile range, periodically they would shoot a missile from Utah down to White Sands Missile Range. And as an example of the machine-generated data, they had a measurement on the rocket of how fast the rocket was going, the elevation the rocket was at, and the location of the rocket. And these were generated like every 10th of a second. So when a rocket shoot occurred, you had a tremendous amount of information arriving to the computer very, very quickly. And this is what you can think of as machine-generated data looking like. So there was this notion then that we should take all of this data and throw it into something called a data lake. And a data lake then is a place where people are going to put data and take that data and then at a later point in time, do something with it. And so the idea was that you take all of this machine-generated data, put it into a data lake, and it makes a nice place for people to come do analysis from. The problem is that the data lake turned into a data swamp. And so instead of having a nice clean lake where people want to swim and have recreation, we have a swamp where we have mosquitoes and no one wants to go. And so what's the problem here? The problem is that we can put all of this data into a data lake, but nobody can do anything with it. Or if they want to do something with it, it's very difficult to do something with it. And so the notion of a data lake, of just throwing data into some repository and calling it an architectural structure, a data lake, turned out to be not a very good idea. Why? Because the data swamp was not good for anybody. You really couldn't do anything with the data in the data swamp. So what do we need to do? We need to turn that data lake into a lake house. And so we see then that there is a need for an architectural infrastructure to be put in over the data lake. And so we say, why do we need to do this? Well, I think it's kind of curious. I've had many conversations with people that are data scientists, and data scientists complain that, gee, I go to school, I learn all of this great stuff about being a data scientist, and then when I go into the world, I find out that 95% of my job is not being a data scientist, but is becoming somebody that fools with data. That instead of being a data science, I become a data garbage man. And that is a gross misuse of the talents of people in data science. So if we have the data lake just sitting there without the infrastructure for how it needs to be put together, we find that we are doing a great disservice to the people that are the data scientists. So what do we need to do to the data lake? We need to add an infrastructure to it to make it usable. We need to turn that data lake into something that we can do analytics from. So how do we go about doing this? Well, the place to start, let's start with machine-generated basic data. And let's talk about what we can do to that data. The first thing that we can do to machine-generated data is to come along and divide the data into data that has a high probability of access and data that has a low probability of access. Now, in order to understand this, let's go back to the missile range and take a look at the shooting of a rocket. When a rocket goes into the air, many measurements on a 1/10 of a second basis are generated. The speed of the rocket, the altitude of the rocket, the location of the rocket. And so a given rocket shoot will generate millions of instances of occasions of data. And yet, when you start to do the analysis of the data, the vast majority of that data is not useful. You only want to look at such things as the ultimate speed of the rocket, the ultimate height of the rocket, and the delivery of the rocket to the right location. So out of the millions and millions of records that we create in the rocket chute, we find that only a handful of those records are really useful for analytical processing. So what do we want to do? If we take all of that data and just put it into a data lake, we're going to make it difficult for a person to do analytical processing with. So what do we need to do? What we need to do is to find the data that has the high probability of access, take that data and turn it into somewhere where we can find it, and then to take the remaining worst of the data and put it into a place where is a a low probability of access, something called bulk storage or some form of low access performing storage. And so we call this segmenting the data. Segmenting the data of our machine data into data that has different probabilities of access. Why do we do this? We do this so that we can start to do an appropriate analytical processing on the data. Now, we mentioned that in our data lakehouse, we're going to have essentially three kinds of data. We're going to have structured data, textual data, and analog machine-generated data. You may be interested to know that in general, the way most corporations work is the relative volumes of data in each sector look something like this. Relatively speaking, there's not that much structured data. When it comes to textual data, we end up having the need for having more data than structured data, but less data than the machine-generated data in the environment. So this is the relative volume of data in each sector. So from a standpoint of working with our data, another consideration is the format of the data. After we put our textual data through textual ETL, we end up with a classical relational format of data. So we can think of the data in the data lakehouse from a format standpoint of the structured data and the textual data being very compatible. But the data off over in the machine environment is anything but in a standard format. And so and when you start to think about doing analytical processing, there's a lot of considerations. One of them is the basic format, but there are other considerations as well. So from a formatting standpoint, this is what our data in the data lakehouse looks like. The other consideration, other than formatting of the data, is the compatibility of the data itself, of the basic elements of data. Are they compatible? And what we find is that from a compatibility of data element standpoint, we don't have compatibility. Now, what do we mean by compatibility? What we mean by this is over in the structured environment, we have usually nice, neatly defined key structures, such as social security number or account number or things like that. But when we go to textual data, we normally don't have nice, neat little keys of the data. Because, for example, when people are talking, people don't have conversations in terms of key structures and things like that. And certainly, when we go over to the machine environment, the structure in the key in the machine environment is something that is yet very different as well. So it's not just a matter of the formatting of data, it's also the compatibility of the content of data. So in order to do analytics, there's got to be some common way in which we can relate the data together. I don't know if you've ever done analytics before, but when you do analytics, you've got to have some way to have a common theme throughout the data, or otherwise your analytics doesn't work at all. The problem is that when you have all of these different kinds of data, there's no obvious, easy way to isolate the common identifiers. However, there are such things in the world as universal common connectors. Regardless of the format, regardless of the comment of data, it is possible to find a common theme throughout the data as well. And thank goodness we have these common themes, because if we didn't have them, being able to do analytical processing against the different kinds of data would be a very difficult thing to do. So what are some of these common connectors that we have? One set of common connectors is geography, time, and dollar amount. Regardless of whatever you're doing, there's always geography. You're always doing it somewhere in this universe. And so you can take data, and regardless of whatever kind of data you have, you can say, this data was done in the United States, this data was done in England, this data came from China, whatever. There's always geography. And the second feature of a universal common connector is that of time. There's always time, that whenever an event occurs, there's always some unit of time when the event occurs. And then for most data, not all data, but for most data, there's dollar amount. We can always say, well, something occurred off over here and it cost this much. And something occurred off over here and it cost this much. So one set of universal common connectors are geography, time, and dollar amount. Now, when we start to talk about humans, when our data starts to talk about human beings, there are another whole other set of common connectors: gender, age, and race. That wherever you are on this earth and you have a person, that person has a gender, and that person has an age, and that person has a race. So there are common connectors when it comes to looking at people. So there are ways to start to connect and to do comparisons across data, even if the data is otherwise very disconnected. So these are what we, and then when it comes to physical objects, we don't use these very often, but occasionally every object has a weight, every object has a color, cost, and size, and so forth. So you say, okay, Bill, thanks for telling me about how I can connect some of this data. Can you give me an example of the usage of a universal common connector? And sure, I'll be happy to do that. Let's start our conversation with healthcare and something called outcomes analysis. Now, I don't know if you know what an outcome analysis is, but in healthcare, when you're talking about people and health and medicine, there's also something called the outcome. So you see, when a doctor does an operation or when a doctor prescribes medicine, the doctor hopes that that's going to cure the patient and make the patient's health better. But whether or not the surgery worked or whether or not the medicine worked is called the outcome. And being able to compare the procedures that are done in medicine, the medications that are given in medicine with the outcome is a very powerful thing. Why is it powerful? Because we can start to judge the effectiveness of medicine. We can start to judge the effectiveness of procedures. And that, in the long run, is going to improve everybody's health. So that's what an outcome is. So how would we go about doing outcome analysis in our data lakehouse? Well, let's take a simple example here. Over here on the structured side of life, we have sales of different medications, things like Prolia, estrogen, vitamin D, Algical, calcitonin, and there are millions and millions of medications that are out there. And so that's one source of information. Another source of information are doctors' notes. Doctors have examinations, doctors have tests that they do, diagnosis, procedure, medication, and so forth. And then over on the machine side of life, we have things like X-rays. X-rays tell us, was the cancer cured? Was the broken bone, how did that work out? Did the bone heal properly, etc., and so forth? So we have three very different kinds of information that we put into our Lakehouse for healthcare. And so let's take a little bit closer look at this. When we take a look at structured data, we can look at it a lot of different ways. One way we can look at it is by state. We can say what medications were produced or bought in the state of Utah versus the state of Massachusetts versus the state of Florida. That's one way we can look at it. Or we can look at it by age. We can say when a certain medication was it bought by people that were teenagers? Was it bought by people that are middle-aged, or was it bought by older people? Or we can look at it by gender. We can say, did men buy this medication more than women, or did women buy this medication more than men? So we can look at our structured data and look at it by state, by age, and by gender. Now this, again, I hope you recognize what we're doing here. We're using the universal common connectors, and we're going to use that to relate our data. Then we go over to our textual data. And here we find medical records that the doctor's written based upon the encounter with the patient. And we can look at, again, that data by state. What kind of medical records did we find in Utah, Massachusetts, and Florida? We can look at it by age. We can say what medical records did we find for people from 8 years old to 10 years old, from 20 years old to 30 years old, from 60 years old to 70 years old. We can look at it by gender. We can say, when we look at medical records, what are the medical records for men or for women, however we want to look at it. And then we can go over to the data that's produced by machines, the X-ray data and other data that we find, MRI data, CAT scan data, and things like that. And we can look at the results that have been achieved, again, by state, by age, and by gender. And by bringing all of this data together. So now you see, we do have a way to start to compare very different data across the universal common connectors. And so now we can start to ask some interesting questions. Once we have this data put together, and once we organize it by state, by age, and by gender, we can say, what is most effective? How do treatments in Utah differ from treatments in Oregon or Massachusetts or Florida? Is Prolia more effective than estrogen? When patients are treated with Algacal, what other side effects are noticed? So when we bring all of this data together, we can start to draw very powerful conclusions that are going to help people become healthier. And I hope everybody recognizes the value of making people healthier. So we now have a way to do to marry both treatment and outcome together by taking all of this different kind of data and putting it together and using universal common connectors. We can now do an analysis of information that we've not been able to do before. And the result is healthier people, longer life, and better quality of life. And again, I hope I don't have to tell you that it's interesting. A long time ago, I did a presentation like this talking about business. And at the end of the presentation, this person stood up and said, gee, I don't understand why this has any business value. And for once in my life, I was speechless. I didn't know how to tell the person that if you didn't understand the business value of this, you don't belong working for a company because it's so obvious the business value of this. And so the value to improving people's health, if that isn't obvious to you, I don't know what is. Now let's take our concept of universal common connectors and go over to the world of manufacturing. Because you see, it's not just healthcare where a Lakehouse can be useful. There's lots of places: healthcare, manufacturing, business, etc., and so forth. So let's take a case of in manufacturing. Over on the structured side of life, we would have information such as sales data, units sold, date of sale, location of sale, etc., and so forth. In textual data, we would have warranty claims. Now, what's a warranty claim? A warranty claim is where something's been sold and the customer comes back and said, I have a problem with what I bought. It doesn't do what I think it ought to do. And so that's what we find in warranty claims. And what do we find over in the analog machine-generated environment? We find manufacturing data, such things as which machine made which particular unit together. And in our data lakehouse, we can take this data and put it together. Now, how can we tie all of this information together? Well, in the case of manufacturing, we have something that we didn't have in healthcare. In the case of manufacturing, we have a specific unit ID for the product that's being sold. And so in structured data, we can say, okay, we sold these many cars. In warranty data, we can say, and when we sold these cars, this was the information that came back to us from what we didn't do right in the manufacture of the car. And over here in the machine-generated data, we have information about how that particular car was made. So we can tie our data together in the manufacturing environment by unit ID. That would be our universal common connector in the machine environment, in the manufacturing environment. So what kind of analysis can we do? Well, we can do some really interesting things once we have this data put together. For example, what manufacturing machines are producing which defects? We can sit there and say, how can we improve our manufacturing by locating which machines in our manufacturing environment are not doing what they ought to do? We can look at such things as what operators. Is it not a machine's fault, but somebody improperly using the machine? What telemetry needs to be adjusted? What do we need to look for that would make us more able to find problems? So these are the kind of analysis that we can do. And when we put this data together, we find that with this data, we are able to improve manufacturing. Now, what happens when we improve the manufacturing process? What happens when we improve the manufacturing process is we produce things more efficiently. And what does that mean? It means that our customers are happier and that our corporation makes more money, that we have a much more cost-effective way in which we can build our information. So this is the effect of building the infrastructure that you need in your data lakehouse. This is what awaits us once we start to take an architectural approach to the solving of our problems. So, and what does that do? That makes a better, happier world, improving the health and livelihood of people. So that is a little conversation about the data lakehouse.
All right. Well, it was a great event, and I personally want to thank Bill for this great introduction and presentation. As I told you at the very beginning of this workshop, Magnimind events will continue, and we will host people like Bill, and we hope to see you soon in the next event. Goodbye. Thank you so
Thank
much.
you.